So, last in-person lecture of the semester. So, let's see. So, quiz 12, like I said, it's going to be today. Well, it opens up right now, and we'll close tomorrow, and cover lessons 30 and 31. Yeah. Like I said, I'll have the lectures for the next week of classes, so 34 through 36. They'll be available, well, actually, they're technically available right now, so if you want to check them out after class, you can. They'll be on Brightspace as well. And the Zoom office hours, I'll have them tonight, but those will probably be the last 6 to 7 office hours. So I'll have the lectures. Yeah, for next week, I'll have my office hours during the usual class time. So just keep that in mind while you're planning ahead, so to speak. So, yeah. Other than that, I don't know. Any exciting Thanksgiving plans? Y'all heading home? Anything crazy? Okay, cool. Cool. So let's go ahead and start our last in-person lecture by talking about the fundamental theorem of calculus part 2. So, given the rate of change of a function f of x denoted f prime, integrating f prime of x gives the general solution. Okay. So the thing is that if we just integrate f prime, then we just get a general solution, no problem. But the nice thing is that if you remember from lesson 28, if we're given an additional data point, well, then we can figure out what that arbitrary integration constant is through the initial data points. So can get particular solution via IVP. Okay. So the thing is that if we're given that additional data point, we can get the particular solution. But if not, well, you really can't. Can't get particular solution, but we can use the fundamental theorem of calculus, which I'll abbreviate as FTC. We can actually get something else out of this. And that something else is this. So if you recall from last time, the fundamental theorem of calculus states that the difference of f of b minus f of a for f differentiable is equal to the integral from a to b of f prime of x dx. So yeah, that's the fundamental theorem of calculus. So what this difference here is, if we take a look at this difference, then this actually has a nice name tag to it. So in this case, we can use the fundamental theorem of calculus to get what's known as the net change in f of x from x equals a to x equals b. Okay. So, a couple nice things to know from this is that if f prime of x takes on a particular sign for all x in your interval, then this net change can actually correspond to a more specific name. So what I mean by this is that, for instance, if f prime of x is greater than or equal to 0 for all x in a comma b, then if we denote this formula here by asterisk, then asterisk will actually correspond to the net increase now. Okay? So, and then similarly, for f prime of x being less than or equal to 0 for all x in a comma b, our asterisk formula will denote the net decrease. Okay? Since in this case, if we have f prime of x is is greater than or equal to 0, that must mean that f of x will be increasing there. And similarly for f prime being less than or equal to 0. Okay? So, taking a look at example 1 to see what I mean by all this, the growth rate of the population of a county is p prime of t equals the square root of t times 4,995t plus 4,230, where t is time in years. So we're trying to figure out how much does the population increase from t equals 1 to t equals 4 years. So what we'll notice is that in this case, well, based off of our numbers, our interval should be pretty quick to see. So in this case, since t is time in years, we end up with the interval from 1 to 4. So that's not too hard to see. And what we also notice is that, well, if we take a look at p prime t, then what you'll notice is that, well, not only is our interval is something on the positive part of the real line, but there's no negatives here anyway. So that should pretty quickly tell you that p prime of t is going to be non-negative. So what that tells us is that p of t increases, which I will write down once my pencil stops acting up. So p of t increases on 1, 2, 4. Okay. So what that tells us is that, so if p of t equals population at year t, then what that says is that ultimately what we're trying to figure out is how much does the population increase from 1 year to 4 years. So we're trying to figure out the difference between the population at year 4 and the population at year 1. Okay? So like I said, this difference here is the net change / increase in population from year 1 to year 4. Okay? So that takes care of that, no problem. So what the nice thing is that the fundamental theorem of calculus up here tells us that the integral, that p of 4 minus p of 1 will then give us will be equal to the integral from, in this case, 1 to 4 of p prime of t dt by the fundamental theorem of calculus that we established up here. So one thing to note here is that even though we're using a different variable, the idea is still the same. So we could easily replace this t with x, and this would mean the exact same thing. Okay. So now that we have that, we have the integral from 1 to 4 of p prime t. So the thing is that if we take a look at this function by itself, well, it doesn't really seem like there's a good way to evaluate the integral of this thing if we take the expression here as it currently stands. So what's one thing we can do to this function here to make this easier to integrate? Go ahead. Distribute? Yeah, distribute the square root of t, right? So since square root of t is equal to t to the 1/2, then distributing t to the 1/2 in both terms here will be 4,995 times t to the, in this case, 3/2, because here we have t to the first, and then plus 4,230 times t to the 1/2. Okay? So as a result of this, well, p prime of t is then equal to this, so we have 4,995 times t to the 3/2 plus 4,230 times t to the 1/2. Okay? So now let's go ahead and take the integral of this thing. So in this case, we will need the antiderivative power rule again. So in this case, if we use the fact that t to the n t is then equal to t to the n plus 1 over n plus 1 plus c, then what do we get? So we get 4,995 times the integral of t to the 3/2, which should, by this rule here, end up equaling what? So using our antiderivative power rule here, what's the integral of t to the 3 halves? Go ahead.
2/5 t to the power 2.
Yep, 2/5 t to the 5 halves. And then plus 4,230 times integral of square root of t, which is go ahead.
2/3 t to the 3 halves.
2/3 t to the 3 halves. Good. So then integral from 1 to 4. So what you'll notice from this is that if we go ahead and simplify the antiderivative before we apply fundamental theorem, what you'll notice is that, well, 4,995 times 2/5 ends up equaling 1,998 times t to the 5 halves, and then plus 4,230 times 2/3, so that will be 2,820 times t to the 3 halves, and then integral from 1 to 4. Okay? So in this case, if we then apply the fundamental theorem of calculus, we then say, all right, so now we have to take the antiderivative, evaluate at t equals 4. So we have 1,998 times 4 to the 5 halves plus 2,820 times 4 to the 3 halves, and then minus same antiderivative evaluated at t equals 1. So we have 1,998 times 1 to the 5 halves plus 2,820 times 1 to the 3 halves. Okay? And then so as a result, you can go ahead and do the necessary mental math and or plug this into a calculator, though I would recommend using a calculator because these constants here are rather large. So at the end of the day, you should end up with 81,678 as your final answer. Okay? Okay? So basically what this number here tells us is that, okay, well, the problem doesn't give us the exact population at year 1 or year 4, but all we know is that between year 1 and year 4, the county has gained 81,678 people. That's all this number here tells us. Okay? So, any questions on that? Okay. So let's move on to the next example. So example 2 says if t is time in minutes, then the velocity function in meters per minute of a particle moving along a straight line is v of t equals 8t minus 3. So we now have to find the particle's displacement from time t equals 2 minutes to t equals 5 minutes. So here we have, for part A, we have to recall a couple things. So recall, so v of t here, this represents the velocity function as the problem explicitly indicates. But here we also need to remember that if s of t is position at time t, okay, so if s of t is position at time t, then what relationship is there between s of t and v of t? So more specifically, what do I have to do with s of t in order to be able to get to v of t? Does anyone remember?
Take the derivative.
Differentiate. Good. So in this case, v of t is s prime of t. Okay? So that's not too bad. Now, for those of you that have taken a physics class before, let's take a look at this displacement word. So if you've seen a physics class before, you probably have seen this word. I'd be extremely surprised if you didn't. So displacement. So I'll go ahead and recall that definition here. So in this case, displacement is equal to change in position. Okay? So that's all that word means here. So in this case, what do we want? So here we want to figure out the change in position. So based off of the thing we talked about in the first page, namely this difference right here. So we want the net change in the function from x equals a to x equals b. So using this reasoning, we could probably figure out the difference we're trying to evaluate here is s of, in this case, 5, because that's our end time, minus s of 2, because that's our initial time. Okay? So then, by the fundamental theorem of calculus, this guy right here, then what we should end up with is that this guy is the integral from 2 to 5 of s prime of t dt. Right? So, now what that says is, okay, so now let's go ahead and say, all right, so since s prime of t is equal to b of t, which in turn is equal to 8t minus 3, that says that ultimately we got to figure out the definite integral from 2 to 5 of 8t minus 3 dt to figure out our final answer here. Okay? So, in this case, we say, all right, well, what's the antiderivative of this thing first off? So if we integrate 8t minus 3 with respect to t, then what do we get? Go ahead.
4t squared minus 3t.
Yep, 4t squared minus 3t. Good. So integrating from 2 to 5, we say, all right, so then if we apply the fundamental theorem of calculus from this point onward, then what's our numerical value to get from this? You can use a calculator if you need to. So in this case, we say, so if we evaluate this antiderivative at t equals 5, we should have 4 times 25, because 5 squared is 25, and minus 3 times 5, minus 4 times, well, let's see, in this case 2 is t equals 2 now, so you have 2 squared is 4, minus 3 times 2. So then plug this all into a calculator, or you can do the quick mental math yourself. This will equal 75. Okay. So that's part A. So that's not too bad, nothing too much different from compared to the first example. But now things are going to get a bit more interesting, because now we have to find the time t naught when the displacement is 0 after the particle starts moving. So one thing to note here is that remember the convention that when the particle starts moving, we always take that to mean at time t equals 0. So just one thing to keep in mind with that. So as a result of this, we say, all right, well, we want to be able to figure out the time such that, okay, if we plug in this t naught value into our position, and then subtract it with the initial position at time t equals 0, we want to say that this change in position is 0. That's ultimately what we're trying to figure out here. So find time t naught, which in this case has to be greater than 0 because we want to focus on after the particle starts moving. So that this equation holds. Okay? That's all that says. So, by similar reasoning as part A, well, that should tell us that this difference here is exactly equal to the integral from 0 to t naught of s prime of t dt, which in turn is equal to the integral from 0 to t naught of 8t minus 3 dt. So, by similar reasoning as up here, well, we have the antiderivative doesn't change because it's the same thing we're trying to antidifferentiate. So we have 0 to t naught. So here's what happens with this part though. So if we apply the fundamental theorem, we then get, alright, so all we're doing here is we're just letting t naught equal t in this part here with upper bound. So we have 4t naught squared minus 3t naught. So that's all the upper bound is. There's nothing much we can do past that. And then from there we just do the usual thing where we let t equal 0 to get 4 times 0 squared minus 3 times 0. So then as a result, that should pretty quickly tell you your equation should be 4t naught squared minus 3t naught. So all that tells us is that this difference here is then equal to this, which, okay, fair enough. But now, we set this equal to 0 as per our assumptions. So, if we set this equal to 0, then what value t naught, which again needs to be positive, will give us the value of t naught we're looking for here. So if we set that equal to 0. Go ahead.
3/4.
Yeah, just 3/4, right? Okay. So that will be part B. So that will be your final answer for part B. So any questions on part B or just example 2? Okay. So moving on to part 3 from this. So this one's going to be a bit similar, at least in concept. So the acceleration of a car t seconds after the driver steps on the brake, before the car comes to a full stop, is a of t equals negative t minus 6 quantity squared miles per hour per second. What's the decrease in velocity in miles per hour 5 seconds after the brake is applied? So before we get into the nitty-gritty of this problem, one thing I should probably mention is that this brake is applied phrase, you can assume that to mean that the brake is applied at time t equals 0. At t equals 0. Okay. So that's one thing to keep in mind for this problem. Another thing to keep in mind is that recall that, okay, if we have the velocity function, then what do we have to do with this to get the acceleration function? Differentiate it again, right? So like I said, it's similar to example 2 in that we have a relationship between the function given to us and the quantity and the function representing the quantity we're trying to evaluate. So in this case, if v prime of t equals a of t, and one thing to note here is that if we take a look at this expression here, and we know, alright, so in this case our interval is going to be from t equals 0 to, in this case, t equals 5, because we're focusing on 5 seconds after the brake is applied. So on 0, comma 5, then what do we notice? So a of t here, is that going to be, will that be taken as strictly positive or strictly negative, if at all? Can that be taken to be either positive on this interval or negative on this interval?
negative?
Yeah, it's going to be completely negative, right? Because remember, we have this t minus 6 quantity squared, so the squared part automatically gives us that just this part here gives us positive, but because of the negative, we get that it's going to be negative here. So what that tells us is that, all right, that means that v of t is going to decrease. Okay? So the net change / decrease in velocity is the following. So here's what we get. So we have v of 5. So that means we have to figure out, all right, so we have to figure out the, based on our interval here, that means we got to figure out the velocity at 5 minus the velocity at 0. So by the fundamental theorem, we have that this is equal to the integral from 0 to 5 of v prime of t dt. So that's equal to integral from 0 to 5 of negative t minus 6 quantity squared dt. So we say, all right, well, how do we evaluate this integral? Because it doesn't really seem like, based off of the techniques we know, there's a nice way to take the antiderivative of this thing. So what would be our best bet from here? What should we do with our function inside the integral to evaluate this thing?
Distribute?
Yeah, distribute it out, right? So if we do that, we say, all right, well, we have negative of, well, let's see, t minus 6 quantity squared. So if you expand that out, you should end up with, well, t squared minus 12t plus 36 dt. So then distribute the negative to get integral from 0 to 5 of negative t squared plus 12t minus 36 dt. So take the antiderivative of this thing, and what should you end up with for that? Go ahead.
I got negative 1/3 t plus 6t squared plus 36t.
Yep. Yep. So we have negative 1/3 t squared plus 6t squared. Sorry. Negative 1/3 t cubed. Sorry. Plus 6t squared minus 36t. And then we go from 0 to 5. So then if we apply the fundamental theorem of calculus on this, and if we use a calculator, if you guys have one, then what should you guys get as what fraction should you guys end up with? Go ahead.
Negative 213 over 3.
Good, 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 good. So in this case, if you let t equal 5, we get negative 125 over 3 because, well, that's what 5 cubed is. We get plus 6 times t squared, so 25, minus 36 times 5. And then, well, noting that if you let t equal 0, this all becomes 0. So So just a big fat 0 for this second part. You should end up with negative 215 over 3 as your final answer here. So what that tells you at the end of the day is that therefore the decrease in velocity 5 seconds after brake is applied is 215 over 3 miles per hour. So basically that's what all this math that we just did in example 3 tells you. So if you want to put that in a nice sentence you can think about, you can. Nice little sentence to think about so you can tell your folks at Thanksgiving, what have you been doing all semester? Well, there's just one thing you can do. So, okay, so any other questions on example 3? All right, coolio. All right, last in-person example. All right, let's do this. So, example 4, the premise is that a faucet turned on at 9 a.m. and water starts to flow into the initially empty tank at the rate of R of t equals 5 times square root of t, which I will go ahead and say is 5 times t to the 1/2 because we already saw that it holds. But now here t is time in hours after 9 a.m. and the rate R of t is in cubic feet per hour. So for A we say, all right, how much water in cubic feet flows into the tank from 10 a.m. to 1 p.m.? So for part A, we say, all right, because of the fact that we need to be able to essentially work with t as time in hours after 9 a.m., we got to say, all right, we got to be able to translate these two times into values of t here. So we have 10 a.m. and 1 p.m. Okay, so for 10 a.m., that will correspond to time t equals what?
Equals 1.
Yep, t equals 1, and 1 p.m. is
Equals 3.
3?
4.
4, right, because remember, noon, you're thinking of noon for t equals 3. Okay. And then t equals 1, t equals 4. So essentially, that's going to be your bounds for the integral you need here. And also noting that since r of t equals 5 times the square root of t, which in this case is going to be non-negative on 1, 4, the increase in water is modeled by, so in this case, it's going to be modeled by some integral. So based off the data we just established, what definite integral do we need to work with here? Go ahead.
It'd be from 1 to 4 of r prime of t.
Well, you have to be a bit careful because remember, in this case, r of t, little r, corresponds to a rate. So that we already have a rate function already.
So it would just be r of t.
Yeah, just r of t. Because in this case, because up until this point, we've been integrating rate functions. That's essentially what's been happening. So and because of this, we essentially have to say r of t dt is the thing we got to evaluate here, which in this case is the integral from 1 to 4 of 5t to the 1/2 dt. So if we take the antiderivative of this thing, then based on what we've been doing up until this point, you should be able to pretty quickly see that this is just 10/3 times t to the 3/2 from 1 to 4. So then if you apply the fundamental theorem of calculus on this, then you end up with, well, 10/3 times 4 to the 3/2 minus 10/3 times 1 to the 3 halves. Okay? So let me make that a little bit cleaner. So we have 3 halves here. And so if you put this into a fraction and clean this up a bit, you should end up with 70/3. Okay? So part A is not too bad. But now part B is where things get a bit more interesting. So if the tank has capacity 92 cubic feet, how many hours after 9 a.m. will the tank be full? We have to round our answer to the nearest hundredth. So what we're going to do now is we're going to let R of t equal amounts of water at time t. Okay? So here's what this says. So we're given some nice things here. So in this case, if we differentiate capital R of t, then that corresponds to the, based off of what we established on page 1 here, and based off of what we established in page 1, then if we differentiate, in this case, R of t, then we should be getting the rate of change of our function. So rates of change in amounts of water. Okay? Okay? So that gives you that. But the nice thing is that, oh, wait a minute. We already have what the rate of change is. The problem already gives us this. That's just little rt, which is 5 times t to the 1/2. So because of that, what you should be getting from this is that we say, all right, so we get r prime of t as this guy, but we also have a nice condition given to us as well. We have another data point. Because if you take a look back at the first sentence here, the problem states that the tank is initially empty. So remember, the fact that we have this initially word should immediately ring that you need to be working with t equals 0 here. So because of that, you have that r of 0 should be equal to what if r of t is the amount of water at time t?
0.
Yeah, just 0, right? Because in this case, this 0 here corresponds to the initial time, and this 0 here corresponds to the fact that the tank is empty. So the initial time, and this is the initial amounts. Okay? So in this case, here's what this says. Part B is asking, okay, if the tank has capacity 92, then we got to figure out how many hours after 9 a.m. will the tank be full. So in this case, we have to figure out some time t naught. So if we denote the desired amount of hours by t naught here, then we want to figure out the value of t naught so that if we plug in t naught into our amount function, capital R, then we want to figure out how many hours t naught will the tank be full. So in this case, we want to be able to figure out when it hits 92. So in this case, we've got to figure out r of t naught equals 92. Okay? So because of this, you say, all right, well, wait a minute. If you take a look at what we're given, what you notice is that we have r prime of t equals 5 times t to the 1/2, but at the same time, we're also given r of 0 equals 0. Huh, that looks like an initial value problem. That looks like an initial value problem, doesn't it? IVP. Okay? So what that says is that, okay, you could use the techniques that we used in lesson 28 to be able to solve this. So we can use lesson 28 methods. So you could do that. Or here's another idea, which we can is just as valid. we can use a fundamental theorem of calculus. So if you want to try using the initial value problem methods from lesson 28 on your own, you can do that. But I'm going to use fundamental theorem of calculus to stress a few things that could be useful here. So here's what we get. So in this case, we have r of t naught minus r of 0, because in this case, we ultimately want to be able to work with r of t naught here. And then because we know what the initial amount is, we can work with r of 0. So in this case, we have this difference here by the fundamental theorem of calculus is then equal to the definite integral from 0 to t naught of r prime of t dt. Okay? So because of that, if then we were to then subtract this r of 0 over to the other side, then we have r of t naught should therefore equal r of 0 plus the integral from 0 to t naught of r prime of t dt. So because of that, what that tells us is that now we can essentially find the amount of water in the tank at time t naught. Essentially is what this gives us. So let me go ahead and write that down. So amount of water at time t naught. So here's what this says. So in this case, r of 0, like we already established, is 0. So this just goes away. And then we have the integral from 0 to t naught of r prime of t, which in this case is 5t to the 1/2 dt. So here's what this says. So if we take the antiderivative of this, well, as we already saw in part A, that's just 10/3 times t to the 3/2, and then going from 0 to t naught. Okay? So then if we apply the fundamental theorem of calculus on this, as per what we did in example 2b, then we have 10/3 times t naught to the 3/2 minus 10/3 times 0 to the 3/2. Okay? So then as you can see, well, this part goes away pretty nice and quickly. So we have 10/3 times t naught to the 3/2 is going to be our t naught exactly here. Okay? Okay. So that's that part. So now, all we have to do now is say, all right, well, we want to be able to get t naught so that r of t naught is equal to 92. So at this point, the last thing we have to do is then solve 10/3 times t naught to the 3/2 is then equal to, in this case, we have to let this equal 92. Okay? So if we go ahead and solve for t naught here, what exact value should you end up with? So let's first start by solving for t naught to the 3/2. So what exact value should we get if we solve for t naught to the 3/2? So what should we do with this 10/3 to be able to move this to the other side?
Divide.
We got to divide 10/3 over to the other side, right? Or equivalently multiply through 10ths to both sides. So we have 92 times 3 over 10. Okay? So then t naught will be equal to what? So we have 92 times 3 over 10 all of that raised to what power? So, if we want to get T naught by itself here, what power should we raise here to be able to get T naught by itself? So, if we have T naught of 3/2, then we want to be able to multiply this by raised to the power of what fraction? To be able to get rid of the 3/2 on this side. In this case, you want to multiply this by 2/3. Raise it to the power of 2/3. Because in this case, one way you can think of it is to say, all right, we have in this case, we have T naught to the 3/2. So one thing we could do is say, all right, well, we could sort of square both sides to get T naught cubed. But then we can say, all right, well then T naught cubed, raise that to the power of 1/3 to get T naught. So in this case, all we're really doing is we're taking this and we're raising it to the power of the reciprocal of this guy. That's all we're doing. Okay. So then T naught as an exact value is equal to 92 times 3/10 raised to the power of 2/3, which is approximately, if you put this into a calculator, 9.1. Because that's the problem states that you need to round this to the nearest 10. Okay. And that's example 4. That's the last in-person example. And that's that. So like I said, this has been an interesting semester, but it's been great being able to teach you guys, even though not a lot of people are here, but that's okay. But like I said, I'll still be able to reach out to me. I'll still have my usual Piazza office hours from 4 to 5 tonight. Last office hours from 6 to 7 are 10 nights. But after that, the next week Zoom office hours will be during the usual class time. And then otherwise, if I don't see you guys at any point in that, I'll just say have a good break, have a good rest of the semester, good luck on finals, all that stuff. And it's been, like I said, it's been an interesting semester being able to teach you guys these interesting times. Let's say see you guys around. Yeah, no problem.